And what was the idea? The idea was that we know a correlator in the planar limit would have some nice 1 over n squared expansion, and we wanted to see if there's something like that at all for the non-planar case. So I took, so first of all I calculate the planar correlator. So we have some operator O1. It's some general multi-trace operator. The number of fields inside the operator is order 1, meaning I hold this fixed as I take n to infinity. And I can expand this in terms of Schur polynomials because I know the Schur polynomials provide a basis. So no problem. I then looked at a second operator O2, same thing. Also, this is order 1. And then I calculated the 2-point function. I did it using the Schur polynomials. So just plug those expansions in. And what's nice about this is we know the Schur polynomials are orthogonal, so we'll get a delta RS, and we'll get this number FR, which, if you remember, is just the product of the factors, these n-dependent things. So that at the end of the day, that's what the correlator looks like. And we know that if we were to expand this in 1 over n, there would be some expansions, sum over I, ci, n to the a minus I. And we could work out what that is. The coefficients here have a nice interpretation in terms of string world sheets, genuses of ribbon graphs, and all of that. So this we understand well. We then wanted to consider a case where we've taken a Young diagram B. This has got a total of m columns and n rows.
Robert, why did you
Yes.
explain that non-planar?
Because in this situation, the number of fields is order 1. So if I was to sum only the planar graphs, I would get an accurate approximation, no matter what O1 and O2 are. In this case, the total number of fields, if you like, appearing inside you when I calculate the expectation value, because m is scaling like n, the total number of fields is order n squared. And if I was now just to count how many non-planar graphs there are, there's an enormous number of them, and they completely overpower the 1 over n squared suppression. So if I was calculating this answer over here, I could not restrict to just planar graphs. I would just get the wrong answer.
In particular, B's of this type of this big B's will come if I have operators which has order n square fields.
Exactly. Yep. So there's order n squared fields. Yep.
Isn't it true that if you already have more than order square root n fields?
Absolutely. So as soon as I go above square root n fields, the planar approximation is no longer a good approximation. Absolutely.
In fact, the number of fields is j, then j squared by n is the true genus counting, right?
Absolutely. Yep. So in this setting, can we now calculate this correlator? And I chose this B because it has some nice properties. So my strategy is going to be the following. Let's maybe do that. I'm going to think about chi b of z times by O1 as a single object. So we've got chi b times by O1, and this would be, I'm plugging in now the expansion for O1. This is chi b and chi r. Now, I picked my b very carefully, and what's special about this b, because it has a total of n rows, if I take the tensor product with some other representation, r, whatever it is, the tensor product of the representations, the character of that is this character sitting here. So whatever representations I get here, this product will be a sum of those representations. What is nice about this product, though, just following the usual Littlewood-Richardson rule, is that only a single representation appears, and it's the representation that I get when I tag R on the side.
So you've chosen a specific big guy.
Exactly. And this big guy, what's important, has n rows. So nothing else I can do. I'm going to call this representation plus R. To remind you, it's the background B together with this R sitting there.
And n is different from n minus 1.
Absolutely, n is
It's
different.
basically just a singlet.
If it was SUN, absolutely, that would be a complete singlet. Absolutely.
Okay. So therefore you get the same. Yeah.
Exactly. Exactly. So what do we get here? This is a sum over R, alpha R, same coefficient, except that now we have chi plus R. So if I now plug this in over here,
Sorry, Robert.
yes,
Precisely n.
precisely n. So I picked a very special Young diagram. Yeah. And
Otherwise you get lots of representations.
exactly. Yep. So now what happens is you can see all of my formulas are going to be exactly the same as they were in the beginning. The only difference is that the characters are these plus r's. So what happens is I will get a sum over r, alpha r, beta r, and f plus r. That's from the numerator. And from the denominator, I will just get fb. Now, what is f plus r and fb?
Sorry, chi b in terms of shoe, polynomial basis is just a singlet.
If it was, okay, so it's un, yes. So
Okay, but it encodes the cell information.
exactly, yeah. So what would I do? I would start to fill up the boxes with the factors. So I would have n plus 1, I would continue. And let's imagine that I've got this r sitting here.
Sorry, we had to remind myself. So we had some explicit expression of FR in terms of n.
That's exactly,
So we just need to calculate the similar thing for f plus r, and then we divide and
exactly,
see the expression.
precisely. That's exactly what I'm doing now. So what the explicit expression was, take your Young diagram, fill an n into the first box, add 1 every time you go across, subtract 1 every time you come down. So this would now be an n minus 1 and fill the entire box. Okay? Now over here we said there's a total of m columns. Okay? So here's a question for the audience. What is the number that sits inside this box? N plus m. So n plus m plus 1, n plus m minus 1. And then these would all fill up fb. So if we look at what's happening here, here we've got f plus r, which would be a product of all of those numbers, divided by fb, which would be a product of all of the numbers except for these sitting out here. So in the end, what do you get? You just get a sum over r, alpha r, beta r, and now if I just look at fr itself would have been n times n plus 1 times n minus 1. So this product of numbers is exactly the same as that one, except we replace n by n plus m. So fr, and I'm just going to say replace n by n plus m. So that means that if you compare what we got in the planar limit to what we got here, it's exactly the same except for that replacement of n going into n plus m. So we now have a sum over I, ci, exactly the same coefficients. The only difference is we've got n plus m to the a minus I. So the net effect of all of these non-planar graphs that you have summed is to change n into n plus m. And that's it. For this very special class of correlators, the coefficients all stay exactly the same.
And you went through this yesterday, but this M completely filled columns is a particular element.
That's correct.
Simple element.
It's what it corresponds to is the annulus.
Right.
So, I mean, let me suggest an interpretation. So the suggested interpretation is the following. You can think about this as a system of m giant gravitons. So there's the m giants. You've got sort of n units of flux from the background. Then you've got these m giant gravitons sitting on top there, and their flux adds to give you this n plus m. So that's sort of what's going on. Now, another check that you could do of this would be not to take O1 and O2 to have just Z's in them, but to start considering something with both Z's and Y's in it. And in that case, you would get Toft coupling corrections, and you can ask, what is the Toft coupling expansion in this case?
So what exact, this is now about the normalization of the two-point function of this new small operator in the LLM background. It's not about the dimension. Dimension is just whatever it was. I'm trying to understand what calculation in ADS CFT I would have to do to verify this n plus n.
Okay. So one of the things that we did was do the usual GKPW type thing where you use the supergravity action to compute correlators, but do it in an LLM background, this LLM background, not the original ADS5 cross S5.
Track of normalizations.
Exactly.
I mean, often one normalizes the two-point functions to unity and then looks at three-point functions.
Yeah.
But you want the normalization of the two-point function.
Exactly. Yeah.
Okay. So you have to work a little carefully.
That's right. Absolutely.
But because these are BPS operators, you can.
Exactly.
And you can compare them.
Exactly. Yeah. So if you take the O1 to include both Z's and Y's in it, they yes, sure.
N plus M, you said, roughly you were saying it's like having an ADS with M more units of flux.
Yes.
But shouldn't we think of these giant gravitons as eating up some of the units of flux?
Well, so I imagine that if you had an excitation sitting over here, that would be the case. But if you had an excitation sitting over here, that would behave differently.
Well, you know, the flux at infinity is always the same. These
Right.
are normalizable states.
Yes.
So the flux at infinity is always in.
Right.
So if you encounter giant gravitons in the middle, it means the flux inside will become smaller. But it's not that the flux will ever become larger.
But then
Right.
M cannot be greater than n.
M cannot be greater than n. Presumably not.
So, well, there's no, in the CFT, there's no cutoff on how large M can be.
What is the map to these
LM geometries?
They'll
Okay.
probably become a singular. You'll probably get a singularity.
Okay, quite likely. So horizontal edges correspond to white regions on the LLM plane and vertical edges to black regions. So moving on the edge of the Young diagram is like moving radially outwards.
Right. It's the net area under the curve is in some units n, right?
Exactly, that's right.
So that tells you that inside you cannot go below 0.
No, so what he said was that in the middle the area is M and the annulus is the area of M.
Yep.
Yeah, exactly. So the total amount of flux. No, it can't be it.
No, I also seem to remember that with every giant graviton, it just goes from, if it's outside it's n, inside it becomes n minus 1.
Oh, so that's true. You mean if you have a giant as you move inside? Okay. Now,
Infinity is not changed.
so
Inside can change.
so that is usually used to, and so when you think about the cutoff on the number of giants, the sphere giant gets as big as the sphere, and then it cannot get bigger. But why? But you can also read this diagram. So you could read it as M sphere giants, or you could read it as N ADS giants. And in that way of viewing it, why is the number of ADS giants cut off? And that's this flux argument. As soon as you've used up all of the units of flux, you can't support another giant. So M giants in total.
So I'm sorry, so it's a dual giants.
It's a dual giants.
Dual
Yeah.
giants are the ones which cut off, they reduce the flux by 1 unit every time.
The giants that got big in ADS, yes.
But you'll never see a region of ADS with more than n units of flux. Units of flux will either decrease or stay the same. I don't
So the giant, okay, so the giant itself is a dipole, right? So the total flux that the giant gives is 0.
Well, but if you're inside, suppose let me think in terms of dual giants, which are
Right.
a bit easier.
Okay, yep.
You've got a spherical D3 grain inside. The net flux outside is n. So if you go inside the D3 grain, Now the net flux is n minus 1.
Yes. Absolutely.
And so, but it never becomes more than n, right?
That's what
So
I say. The total number of rows
is fixed
is
to n.
Okay, all right, but he's interpreting this n plus m as an effective
That-
flux. I can't
yeah.
understand.
Also, the
Oh, yeah,
area of
that-
the
Okay.
full circle is L plus M, you said, right?
Sorry?
The area of the full circle is also L plus M, you said, right?
This full area is m plus n. So if you were sitting over here, I mean, I was thinking and probing locally, how would you know the difference between this and something that's filled? So maybe that picture is not.
Yes, you're saying it's not the flux, but somehow the geometry.
Yeah, yeah,
Maybe something like that.
yeah.
Maybe.
Yeah.
So
Okay.
let me answer. The total area of the hole inside is that's what that's
Yeah. The whole
Yeah.
thing is n plus m,
Yep.
but only this part carries charge.
so
Exactly.
M fermions are scooped out from the middle
Exactly.
and put up.
Exactly. Yep.
okay.
And you can see all of them are excited, all of them. How much are they excited by? Each is excited by m units.
Right.
So you've got a total of m empty states, and that's that area of m in the middle.
So, and you've done a check with area set, you say you calculate and you get the same answer?
Yes, that was
Very impressive.
that was using this GKPW with the dictionary that Skinderis Taylor set up.
Okay, great. So you use GKPW, you can work in this LLM geometry, you can
Yes.
do the calculation.
Well, Skinderis and Taylor can, and then we just use their results
So
basically.
you have to solve a wave equation.
Absolutely.
And you are able to do that.
They have done that.
Okay.
Yes.
Okay.
Yep.
That's very good.
So the
Um,
radii of the S3s, I presume, they will depend on n plus n. But the flux,
Yeah.
the RR
Yes.
stuff,
Yes.
that will remain n.
Yes.
Right?
Yeah. Okay, then the only other comment I want to make, so I'm not going to go through this, it gets messy, but if you replace O1 and O2 by operators that have both Z's and Y's, then in the CFT you do have Toft coupling corrections. And what you might ask yourself is, what is the Toft coupling, the natural Toft coupling? Is it G mul squared n, or is it G mul squared n plus n? And the answer is, the natural Toft coupling that you get is G mul squared n plus m. And I thought that was nice. It's similar to what happens in BMN, where your genus counting parameter looks like j squared over n, but then the Toft coupling also gets rescaled by this j squared. So really j squared over n is an n effective. N plus m is playing the role of an n effective here.
The first thing you're saying is that the, wait, so this is the Toft coupling, I see.
Yep.
And what about the genus? How, is there an effective genus expansion?
Well, I can read off what I had in the planar limit and identify. So as much as you want to believe that is an effective genus expansion, there is one.
Meaning terms of N plus M.
Yes, exactly.
1 over N plus M.
1 over n plus m, that's right.
It's very nice.
So you mean to say 1 over n plus m whole square, 1 over n plus n whole to the power,
For
etc.?
exactly. So the point is, I mean, the reason why I'm mentioning the simple example, I'm sure there's lots of things that could be clarified, but this is one example where you sum up all of these non-planar diagrams, and the effect actually is not too bad. It just changes n into n plus m. So maybe there's some hope that there are some things that are simple for some cases. Of course, it's a very special B, and if you don't pick this B, things get very messy, but anyway.
It's reasonable, right? Because you still have a classical supergravity background.
Yep.
The coupling constant is still, in some sense, 1 over n. But then the radius has changed a bit and so on. So
Right.
some order 1 effect. This is some order 1 connection.
Right.
Sounds reasonable. But the Toft coupling, it sounds very interesting.
But in general, non-BPS observables in this background would not just mimic the EDS background, right? With
No.
this
That's so not such a simple relation. Yeah.
The wave equation is totally different. It's
Yeah.
completely different.
But the 2-point function you would have expected to be the same.
But just for this, probably for this BPS operator,
Exactly. That's the only guys.
it's simultaneously supersymmetric with the background. Somehow that is important. I think you just take a minimally coupled scalar, random minimally coupled scalar, behave completely different.
Yeah.
So
Yeah.
even for the free theory, it would be different for
Uh,
Y.
Absolutely. Yeah, yeah. Okay. So that was, just to give an example, where we were actually calculating something in the, something that wasn't planar. So I want to move on now to, so far we've only talked about one matrix, and in the case of one matrix, you have a free fermion description, so you could actually have done all of this using free fermions. Let's go to two matrices where actually there isn't a good method to calculate. So now we'll take two matrices, and what can we do? So again, let's imagine we've got some fields Z and Y, and I'm going to take n Zs and m Ys. And once again, I can label this by a permutation. And again, it's redundant. Now, in the case of the Zs, we had a redundancy because we could swap two Zs because of bosonic statistics. Here, the redundancy is a little more intricate, a little bit more. We can swap Zs and we can swap Ys, but you can't swap a Z and a Y. So actually, the redundancy that you have here, so the redundancy is Sn times by Sn. So what's going on? There's some interesting interaction between two things. To make something that's gauge invariant, we don't care if we contract a Z and a Y. So from the point of view of gauge invariance to get a singlet, Zs and Ys count the same. But from the point of view of bosonic statistics, Zs are invariant and Ys are invariant under swap separately.
Trace
So
Z squared, Y squared is not the same as trace Z, Y, Z, Y.
exactly, exactly. But they're both gauge invariant. Yep. So that's why we need Sn plus m, because the gauge symmetry doesn't care. And this is why we need Sn times Sm, because bosonic statistics does care. So what we would now like to do is, so if I take trace of sigma z tensor n, y tensor m, equal to trace of sigma 2 z tensor n, y tensor m, then what condition must sigma 1 and sigma 2 satisfy? Well, it turns out sigma 1 must be equal to gamma, sigma 2 gamma inverse, so conjugation, but you're only allowed to swap Zs and Ys. So where do these sigmas belong? In fact, the complete set of sigmas, the complete non-redundant set of sigmas are in a coset Sn plus m, and just mod out by that action. So identify everything related by that kind of a conjugation. So what we'd like to do now is let's do a Fourier transform, but to this coset. That's what we did with the Schur polynomial.
It's conjugate, by conjugation.
Exactly, precisely this.
Not
Yep.
by left action, right?
No, not by left action. Yeah. Yes, not by left action. Good. So how do we do that? Well, what we have to do is we have to take our representation. So we're going to have a representation R. So R is a partition of n plus m, so it's some representation of Sn plus m. And we want to restrict to Sn times Sm. And when we do that, the representations now will be labeled by a pair of Young diagrams, and R will have a total of n boxes, and S will have a total of m boxes. And then what we want to do, all of these things are going to play a role in the game, and I'm going to show you the thing that plays the role of the character. But before we do that, there's a subtlety here that's important that we must take into account. And what that subtlety is, when you restrict to the subgroup, representations of the subgroup can appear more than once. So let me give you an example. So this is actually the first example where this appears. So here we have S6. So we could be thinking about m is equal to n is equal to 3. And then what I have to start doing is I have to say, well, this S6 representation, how would it behave under the S3 times S3 subgroup? And the reps that you get, you would be able to get that. Direct sum that, and you could keep going. But what is important is this representation appears, but not just once, it appears twice. So now you not only have to keep track of which representation of the subgroup you are talking about, you also have to you have to talk about which copy of that representation. It may appear more than once. So we're going to need a multiplicity label now as well. So I'm going to put here gamma, and gamma is a multiplicity
You want to write down everything in terms of characters of this coset.
Yes.
So this, so we want a transformation between this coset and something
Traces.
Like, yeah, something like chi-B object. So earlier chi-B object was
So, okay.
related to character of whole permutation group.
So, okay, so this is what I'm going to want. I want something over here which is labeled by a permutation, Z tensor N, Y tensor M. I know that if I pick all of the permutations up to that conjugation, so I make a complete list, I will have a complete list of gauge invariant operators. So this is just like the story with the Z's. But that list is not great.
So this sigma belongs to the coset here, the one that you
Sigma would be an element of that coset, absolutely. Now this list is not very nice for studying the physics, basically because as soon as you have n fields, well, n plus 1 fields or more, not all of these are going to be independent. And taking account of the trace relations when you've got two matrices is much more complicated than trace relations for just a single matrix. So what we would like to do, for the case of just one matrix, we went to this Schur polynomial that was labeled by a representation. I now want to move to a new basis, and my operator will be labeled by the representation R of Sn plus m, telling me how all of the fields were put together to make the gauge invariant guy, if you like. I will also have a label for R and S. This is for Sn and Sm. And then actually, I need a pair of multiplicity labels. And the reason why I need a pair of multiplicity labels, so this is the transformation that we're trying to make. That would be like the trace basis, and this would be the representation theory basis. What this thing is defined as follows. So it looks very, very similar to the Schur polynomials definition. So chi R, Rs, let's say alpha beta of Z and Y is equal to, so this is just a normalization. We will have a sum over sigma is inside S n plus m, so a sum over the full group. And now I'm going to introduce a character that we call a restricted character. And what the restricted character is, by definition,
character in the coset?
no. So what it is, you restrict the trace to this subspace, but you can restrict the row index to a different copy to what you restrict the column index. So what it would look like is, it would be a sum from, let's say, I is equal to 1 to the dimension of R times the dimension of S. That's the total number of states inside the space RS. And then we would have RS, the alpha copy, I, so now we're summing over the states.
Alpha and beta run over the multiplicities of the pair RS.
Exactly, exactly. Exactly. And in fact, if alpha is not equal to beta, this isn't really even a trace. You're not even adding things that are on the diagonal. It's some off-diagonal block that you're adding things in. But the reason why you define this is that these guys, so we call these restricted characters. You know, I really shouldn't have written this. I mean, it's not a normal coset. It's not a left action. This is what we call a restricted character. What's nice about them? All of the usual orthogonality relations that you have for characters, you have for these guys too. So the fact that if you were to sum over all of these representation theory labels, they are usually, you get orthogonality in conjugacy classes. Here you get orthogonality in restricted conjugacy classes. So under this conjugate restricted.
What is the representation theory index for the coset? I'm saying that if you take a representation of the coset, so that coset will have labels of the, that representation will have things like R, capital R and S, because you want representation of the coset. And then if you want to calculate character of sigma in that representation of the coset, it is different than that.
I know.
Specifying that R is, gives you a block, small block, okay, or defined by the dimensionality of the block is that quantity. And he is allowing off-diagonal elements in that block as well, not only diagonals.
Capital R is a representation of the Sn plus m.
Correct.
So if I want a representation of Sn plus m by Sn cross Sn.
But okay, sorry, but this really, I'm dividing out the conjugate action. So let me in fact, I should never have written this.
Yeah.
Let me. So what I'm doing is the space is you go through Sn plus m. Pick up the complete set of sigmas that can be related in this way. Keep that aside. Now pick another sigma and do the same thing. This is an equivalence relation, so this will define some partition of Sn plus m. Each of these we would call a restricted conjugacy class, and we're looking at the space of these restricted conjugacy classes. That's what the space is.
I'm going to try to say it.
Great.
I understand. Please correct me.
Perfect.
Okay, so I've got this this R, the representation of the permutation element sigma in representation R. This is some big matrix that acts on a Hilbert space.
Yep.
Okay. Now this Hilbert space can be broken up into sub-Hilbert spaces. The Hilbert space on which it acts, the vector space on which it acts, can be broken up into sub-vector spaces which are labeled by RS and degeneracy in RS.
Perfect.
And now what you're doing is taking the part of the matrix R that has RS here, RS there, but any one degeneracy label here, any one degeneracy label there.
Exactly.
So this is some square matrix,
Yep.
and you're computing its trace.
Exactly. Yeah.
Why do we get a dr minus ds for the range of things?
Oh, why is it dr times ds?
Oh, it's times.
Yes. Sorry. No, that's yeah. Times. Sorry. Dot. Yeah.
What you said, where is alpha and beta?
Alpha and beta are the degeneracy labels. So there may be 5 copies of a particular RS. Okay, so you could take the first copy and the third copy. These are all different square matrices.
Yes, but then that you are specifying either first or third copy, right? Why alpha and beta?
Because you've got a big square, big matrix, and then there are many square matrices in the middle, and you take each of them. They don't have to be in the diagonal.
Let me just draw this picture. Maybe this will. And it would keep going. And then
That's a 4 by 4 matrix.
exactly, you're allowed to take the trace there, or there, or there, or there. Yeah. And that must be done to get a complete set. So that's the definition of this restricted character. They're not trivial to calculate. So that's your operator in terms of this character. Now, what properties does this operator have? Well,
By the way,
Yep.
is there something that we are familiar with? This is like the spherical harmonics, but with the degeneracy label. So maybe for higher groups, not for the S2, but rather S3, let's say.
Yes.
Is there a degeneracy label also that comes out for
Ah.
spherical harmonics?
Oh, I don't know.
S3 there's no.
Yeah.
S3, thinking of it as SO4 divided by SO3. So representations of SO4 when decomposed into SO3 do they need degeneracies?
No, it's like it's SU2 times SU2, one way of thinking of it. And the answer is that it's J times J. So there's no degeneracy.
But even higher also?
Higher, probably, possibly.
Yeah. Yeah. Yeah.
And then one has to do this kind of.
I guess, yes. Yeah. So first thing is, okay, so these multiplicities, by the way, so let me tell you what they are, because we know what they are. If you are in UN, so let's maybe put this here. If you are in UN and you take a tensor product of two UN representations R and T, you'll get a sum of UN representations S, and they appear a certain integer number of times. That's just the Littlewood-Richardson number. If you take a representation R,
I'm sorry, Rob.
yes,
You've defined this. This is some well-defined operator.
exactly,
And now you're going to tell us what good properties it has.
exactly, yep, absolutely. And all I'm telling you right now is what's the space of those labels, the alpha, the beta, yep. So that's the Littlewood-Richardson number. It tells you how tensor products in UN compose. I mean, you take a product and decompose it into irreps. Now, what you can also do is
I'm sorry to keep interrupting, but
Sure.
you're going to tell us this is a complete set of all gauge elements?
complete set. The trace relations are precisely given by restricting the young diagram's rows to have no more than n rows. And then I will also show you these guys start to mix because they do get Toft coupling corrections. They're not BPS.
That's fine, but just
Yeah.
the free.
At the level of the free theory, two-point function is orthogonal. They're a complete set. They take into account trace relations. When you start to add coupling constant corrections at L loops, operators can only mix if you can shift around L boxes. So the mixing is weak.
And the generalization to having M letters is trivial. Right?
Exactly. Yep. It's a little bit tricky to put in fermions, but that can also be done. So if I take this this representation of Sn plus m, and I restrict to Sn times Sm,
I'm sorry to keep interrupting.
no problem.
Does this way of thinking allow you to count?
Yes, it does. So in fact, what I'm going to write down something here, and then I'm going to tell you if you calculate the matrix model for two free matrices and just do the counting, similar to the way that you did it, you get the same answer. And you're summing the squares of the multiplicities because you've got alpha beta, so the sum of the squares of those multiplicities exactly gives you the matrix model partition function. Yep. So if you restrict now to a representation R of Sn and a representation S of Sm, this will decompose. And what does it decompose into? In fact, this is the same number. The Littlewood-Richardson number tells you how these restrict. So for example, if I take this tensor this, I can build that in two ways. So if I was in UN, if I take this tensor this, I will get two copies of that and a whole lot of other stuff. And in Sn, if I take this and restrict, I will get two copies of that. So this is the what these multiplicity labels are. They're determined by the Littlewood-Richardson numbers.
The thing that goes one way in SUN goes the other way in.
Exactly. And this is Schur-Weil duality at work. Yeah.
Right. So there's a version of the Schur-Weil duality with this SN-SN.
Yes, there is. Yeah. Now, so what is the total, if you wanted to calculate the total,
True duality being the exchange of the Sn of this permutation and the while that is sitting inside the
it's
UN.
this commuting action of un and Sn on the space V tensor n,
In
and
particular means
it has all of these consequences, yeah.
But in particular, so suppose I take the same V tensor n as before,
Yep.
where n was m plus n.
Yes.
And now I try to write down what my state, I decompose the Hilbert space
Yep.
in representations of Sn, Sm, and Un.
Yes.
Un. I suppose what you'll get is every Un representation will be associated with all the Sn and Sm representations that you get from decomposing that particular Sn.
Absolutely.
Okay.
Yes.
Alright.
Okay, so now, if you wanted to count these guys, how many operators are there? Well, you would have to sum over all of those labels over there. So we would have a sum over R, a sum over R, a sum over S, and then we would have the multiplicity label, but we know what each multiplicity label runs over. It'll run over FRS. So we would get an FRRS squared. Then let's have a parameter, maybe X, to keep track of the R's. So this would be the number of boxes in that Young diagram. You can have Y, number of boxes in that Young diagram. And you can prove that this thing is equal to the partition function that you would get if you just counted 3 BPS operators in the 2-matrix model. So that counting works out. And by the way, this is not the large n counting, this is finite n counting. Each of these Young diagrams is restricted to have at most n rows. So
Right. Even the matrix model is finite n counting.
exactly,
So-
exactly, absolutely, yep.
Sorry, can you explain this box once more? Just
Sure, this box.
yeah.
So what's happening is, I just want to count what is the total number of restricted Schur polynomials.
Right.
So I would need to sum over all possible labels for the restricted Schurs.
Yes.
So I've definitely got label R, R, S, but I've also got the 2 multiplicity labels.
Yes.
And I'm going to want to sum over those explicitly. Each multiplicity label goes from 1 up to FRRS. So a sum of multiplicity label gives me FRRS. Another sum of a multiplicity label gives me another FRRS. So that's the sum of that squared. That's the multiplicity label sum. And the matrix model spits it out in this form if you manipulate it correctly.
There's some formula for this FRRS.
Exactly, yep, yep.
Goes beyond fusion.
Exactly. So now let me just tell you what does this formula look like for the restricted Schur. So if you take chi r rs alpha beta of z and y, and you take chi dagger, let's say t u gamma delta of z comma y, then this is equal to, so we have the product of the hook lengths for R. So if you remember, go in at the bottom, out at the side, each box gets a number, which is the number of boxes you go through. Take a product of all of those numbers. A product of the n's, the n, n plus 1, n minus 1, and so on, divided by hooks for little r, hooks for little s, and then there's a delta rt, delta little r, little t, delta su, delta alpha delta, delta beta gamma. So it's orthogonal on all labels, and there's a very explicit formula for what that coefficient is. There's also a concrete formula for how do you write any trace in terms of a restricted Schur, but it uses restricted characters, which are not very easy to calculate. Yeah, and it gives you the finite n counting.
The dimension formula, the hooks appeared in the denominator.
Yes?
Okay. And what is that hooks? R doing that?
So this hooks R, So for example, let's imagine that we took something with a Schur polynomial calculating a two-point function, and it has these labels. So the big Young diagram and two little ones. The big Young diagram determines all of the n dependence. That's FR. The big Young diagram will put hooks there, and both of the little Young diagrams contribute a value of hooks in the denominator.
In the limit number of y goes to 0, you just recover the hooks cancel.
Exactly.
You get one.
Precisely. So when the number of y's go to 0, that disappears, these two cancel, and you get the Schur result. Yep. Yeah. And the trivialization to any number of matrices is immediate.
Well, I'm going to ask what's probably an ill-defined question. Let me ask it anyway. In the case of one matrix, there's a basis of polynomials whose Fock space generates all of them. That is trace z square up to trace z to the power n.
Yep.
One.
Yep.
You have these, and then you do multi-particling of these, and you get everything.
Right.
Is there something? I suppose life is not so simple. Let me ask. Is there a finite set of polynomials such that their products with some well-specified relations generates this whole space?
Don't know. So we have tried to approach this question in mimicking again what happens for Schur polynomials. So for the Schurs, there's a very nice formula that you can write, where you can write any Schur as a determinant of things that only have one row. So you change the length of the row, take a determinant, and you can build any representation R. There's another formula where you can take Schurs with only a single column. So in this representation theory language, the set of Schur polynomials with just a single column but any number of boxes would be a basis from which you can build anything, or Schurs with a single row in any number of boxes are a basis from which you can build everything. We would love to know what's the analog of that for these restricted Schurs, but trying to mimic the way things work for Schurs, I mean, we just don't understand these restricted characters well enough.
Using plethysticks, one can probably get the generators and the relations systematically and try to see whether this terminates.
Yeah.
You would do the integral, take the plethistic log, and see whether the log terminates, right?
We have not tried that, so that might give a useful hint. Yeah.
Maybe it doesn't terminate, but there's a pattern of relations.
Mm-hmm.
That one can identify.
Yeah.
Yeah.
For SU2, you can probably work it out, right? For SU2, adjoints are vectors.
Yep.
So form a gauge invariance is actually secretly doing a vector module.
Right. Right.
Which even I do.
Right. Okay. So those are the restricted Schur polynomials. What?
Can we specialize to one y, just one y, single y? Then the S is always one, right? Just
Oh yes, one box. The S will always be one box. Yes.
So this simplifies.
So okay. If you specialize just to one y, then that of course would always be a 1. That could still be something.
No, but this chi and essentially will just be labeled by
Oh,
small r.
the character. That's correct. If in fact, so if you specialize to just having 2 rows and nothing more, then there is no need for the multiplicity label. So 2 rows with any number of z's and y's, no multiplicity label.
So let me ask one more question.
Yep.
The fact that when you take n to infinity, but you keep the number of operators, the size of the operators fixed, the fact that you get a Fock space is essential to having a free picture in the bulk.
Yes.
Now, suppose you take your operators to have order n fields, so that the bulk is d-branes.
Mm-hmm.
Intuitively, you expect d-branes to continue to be free in the bulk at large n, because the mass of a d-brane is 1 by g.
Mm-hmm.
Newton's constant is g squared.
Yes.
So the interaction energy is g squared times 1 by g times 1 by g, which is 1, which is an order 1 by g, order g fraction of the original. So intuitively, d-branes are more interacting than strings, but still non-interacting at large n.
Right.
So this leads me to suspect that some sort of Fock space should work even for operators of dimensions n. At least that the violations of this Fock space should be small. So to do something exactly seems up to Friedrich.
Yep.
But to take large n and to look at operators with scale like, let's say, n,
Yes.
and to see whether their spectrum can be generated as a Fock space, sounds like a physically useful question.
Right.
Could one tackle that?
So let's see. So when you say this Fock space structure, are you thinking about a Fock space for d-brane states or open string excitations of a d-brane?
Well, I was thinking of Fock space for d-brane states.
Okay.
So if you take states with energies 20 times n,
Yep.
I should be able to build them out of products of states with energies n 20 times.
Right. Right. Okay.
I mean,
Yeah.
it's very roughly said, but so that you've got one d-brane doing whatever it's doing, and
Yeah.
another d-brane doing whatever it's doing,
Yeah.
and they're not interacting.
Yeah.
For half PPS, I think you can do that.
For half PPS, it's very easy because trace z to the power. You have a Fock
Anyway,
space.
yeah.
For half BPS planar.
No.
No?
Literally. Trace z squared, trace z cube up to trace z to the power n
Yep.
forms a basis. And
Yeah.
every gauge invariant can be written as a polynomial in this.
Okay.
So you've got the Fock space.
But let's see. It usually it's not a free Fock space.
Well, it's free in the sense that it's
So-
yeah.
But multi-traces are no longer orthogonal under the two-point function.
The multi-traces are not, all trace identities are taken into
Yeah.
account by terminating these the traces.
Right.
So
Right.
there's no further relations. This is a completely unrestricted space. It is just a Fock space.
What's the inner product on this Fock space?
That I don't know.
Okay.
But at least for the purpose of just counting states,
Right.
it's a product of a single particle.
Ah.
It's a Bose exponentiating a single particle Hilbert space.
Right.
Something
Okay.
like that should continue to be true up, not all the way to energies n square,
Right.
but some intermediate energies.
Right. Right.
I think
Yeah.
it would be really interesting to know
Yeah.
whether
Yeah.
it was true,
Yeah.
and then what it is a Fock space of,
Yes.
because that would give you the single d-brane Fock space, Hilbert space.
Right.
Could you use
Right.
your techniques to try to address it?
Interesting. Actually, I haven't thought about it like this, but that's a good question. Yeah.
Okay.
Okay. So what I would like to do now is just to give you an idea. So now we can start to study. Yes?
Citations.
Oh.
You should take that.
And then form a product for Fock space of this.
All those excited. You've got one excited friend, another excited friend.
So I want to look at, so we've done everything in the free theory. So now let's just look at anomalous dimensions. And I just want to give you an idea about how these operators mix. And question? No. And I want to give you an idea about how these operators mix. And do they mix a lot or not so much? And I'm going to work only in the SU2 sector. It's simplest. And in this sector, what do we know? So let's use the explicit form of the dilatation operator. We've got a z and a y, a commutator ddz, ddy. And what we would like to do is act with this operator on a restricted Schur and see what do you get. And
Both numbers are conserved.
sorry?
Both numbers are conserved.
Absolutely. Both the number of z's, both the number of y's are conserved. So you immediately get a beautiful dissection of the space into definite NM sectors. So already that's some mixing that's not going on. But then, but that would be automatic. That's a property of D, not the restricted Schur, so we can't claim too much victory. But if this now acts on the restricted Schur, how does it act? So what's important, let me just stress one thing. G angle squared, trace, zy. In fact, let me not put the trace. Let's put ij. So I'm just going to write out indices for one thing. and there'd be a second term. And the only thing that I want to draw your attention to, if I take this, so this is one loop. If I take this at one loop and I was to act on a Schur polynomial, the y is going to act on some field inside the Schur polynomial, and then the z will act on some field inside the Schur polynomial too. And what's going to happen is this index k gets set equal to that index k. And that's a crucial thing. And let me show you what that lands up doing. So I just want to flash one formula. There's just one specific thing that's important. So D on, I'm going to look at a specific restricted Schur. Now, I've manipulated things a little bit, so I don't just have simply the character anymore. This is the cycle that swaps indices m and m plus 1, and then I have a sigma minus m plus 1. So this is just some manipulation. Here's the important piece. Now, the commutator gets sandwiched in here. But now we've got a delta function. And this delta function came from the shared k index. And what that delta function is, it's a delta of m plus 1 I sigma m plus 1. So I've relabeled a little bit. And then we've got the remaining z's that the derivative didn't hit. What does this delta function do? It means that when we sum over Sn plus m, actually we're not summing over all permutations because m plus 1 has to stay where it is. So this sum actually now becomes a sum over Sn plus m minus 1. So in fact, these representations R that I had here, that's not what's important. What's important is when I restrict R, what representations do I get of Sn plus m minus 1? And when I start rewriting this thing in terms of another restricted Schur, the labels no longer have to match. The labels only have to match after I've dropped one box, because it's the subgroup that's important. So because of that, we're now allowed to mix two restricted Schurs that differ by the position of one box. If you went to AL loops, there would be AL such derivatives. We would restrict to an Sm plus m minus AL subgroup, and you could allow AL boxes to move around. So I think that this is about as constrained as the spin chain picture. So in the spin chain picture, you had a trace, you had a z and a y, and at one loop, you're allowed to have one flip. So it looks very local. Not much can change. Hardly any traces mix. Here, only Schur polynomials mix if they differ in the placement of a single box.
So single box
at one loop.
big R, small r, small s.
Good. In actual fact, all of them can change. They're all allowed to have one box shifted around, and you can shift it around as you like. So it's not easy to see a pattern. I'm going to start taking into account large n.
You are going
Yeah, I'm going to take into account large n where things actually simplify. Things become simpler then. So this is pretty local in the sense that only a single box is moving. But what you will see now, yeah, it gets even more local. Yeah. So the point is,
This is
yes.
correlated, right? If you change the one box from big R, you cannot arbitrarily change the R.
Absolutely, it is
has to
correlated.
be, part of this.
Absolutely,
calculation.
absolutely. Yep. So it's highly constrained.
And this box can be moved around from one place to another without restriction?
Yes. So it can move from one row to the other row, no restriction.
What happens to alpha beta? Because after
Absolutely. So alpha, beta appears inside this big matrix that you calculate, and then you have to diagonalize it. So we spent about a year. I had 2 MSc students. We took, I don't know, we had examples like with 360 operators, and we built this matrix. And then we diagonalized it. And the shocking thing is all of the eigenvalues are integers. I'll show you in a moment why that happens. But we just built them by hand with the multiplicity labels, diagonalized the matrix, got integers. So I actually thought we were having a lot of fun together. And when you get integers coming out, I mean, this to me seemed like it was amazing. But they both left physics after their MSc. They both left physics, yeah. So, I mean, it was technical calculations, I guess. Yeah.
If you restrict, if you're at large n, you restrict. Well, how these chi's in terms of single traces are not. Suppose I take small representations.
Yep.
And n is large.
Yep.
Even then, chi's are mixtures of single and multi traces.
Absolutely.
So there's to go back to a single trace basis is some work in terms of these chi's, right?
Absolutely.
So if I wanted to make contact with the old spin chain literature,
Yep.
even in the case where that applies,
Yep.
it's some work.
Absolutely. It's a lot of work. Yep. Yeah.
This, yeah.
Yeah.
This deals with short operators, right? Spin chain usually are long operators.
Oh, so you can have long things here too.
Yeah.
But it would become really horrible to calculate the.
IR basis, you would have small traces also. Right?
Exactly. You'd have everything mixed up. Exactly. Everything would be in there.
I mean, even
Yep.
the chi with 2 boxes is
Exactly.
z square plus trace z,
Exactly.
the
Yep.
whole square.
Yeah. Yep.
So this is not somehow very natural from the point of view of Fock space.
Yeah.
It's natural from some other point of view.
Yeah.
It would be nice. Is there a clean disentangle in the case where the operators are small
Mm-hmm.
and n is large? Is it easy to go between the single trace bases in this?
No. If you have one y or 2 y's, we've worked it out just by explicit calculation. Beyond that, you mean actually having the explicit formula for the one in terms of the other?
Yeah, I have
That's-
the properties for the
Uh,
matrix that goes between one.
so we can write a formal formula. The coefficients of that are these characters.
Okay. Okay. It just seems from the point of view of Fock space,
Yes.
the traces are better.
Yeah.
So if you're in, if you're at small number of operators and n is large, that seems like a more natural thing.
Absolutely. So yeah, I would agree.
So it would be very for any two probably, because traces don't mix.
Yeah.
So it seems like that's very natural from the point of view of one point of view. This
Yeah.
is natural from the point of view of taking account the trace relations.
Exactly.
It would be nice to be able to jump
So-
between them more.
Yeah. Yeah.
At one loop, I think it will not change the trace. The trace will just go to trace, right? At one loop.
Well, you see, even at one loop now, you can break and put traces back together as long as you have enough fields, because the number of ways of sewing a vertex into your operators explodes with the number of fields. So you're allowed to change the number of traces appearing.
No, but that's for subleading in one way. Right?
No.
Leading order,
At leading order, there's mixing of traces.
no, at one loop.
Yeah. Roughly speaking, if you're going to mix 2 traces, you're breaking one index loop. But if there's square root n fields here and square root n fields here, you have something like square root n times square root n ways of doing that. So you make up for the index loop you lost.
Yeah.
Navijit was saying that
Yeah.
if the number of fields was fixed.
Oh, are you fixing the number of fields? Oh, okay, right, absolutely. Then the number of traces is conserved. Yeah. Okay.
So just to
Yeah.
go back to Shiraz's question about the basis of the Fox space kind of thing.
Yes.
So is it like the so I remember some works by your group about 3-point function of Schur polynomials.
Yes.
And this kind of the interactions, vanishing interactions at large n
Yep.
does show up in some way in 3
Right, right.
And I don't remember the details anymore, but that would be some kind of thing saying that D-branes are still free objects. Okay, and it showed up in some 3-point function of Schur polynomials.
That's right.
So that would seem to say that the Schur polynomials are the right, creation operators for these D-branes, rather than.
So these were close to maximal giants, and if you take the 3-point function, it actually starts to vanish exponentially fast within.
Because a D-brane action is e to the power minus 1 bench.
That's exactly what it is. Yes. Yeah.
Right. I see. But that's not the kind of
Argument that Shirada was giving, right? About the binding energy being smaller than
Even
the
for
rest
these
mass.
shoes, I want to see a Fox space.
Uh-huh.
For him, one shoe and the double shoe are just two different shoes.
Exactly.
But I'd like to see them as product of the.
But
Yeah,
you're
yeah.
mentioning some shoots which are like shoots of smaller things with one or two rows deleted and so on. Are they like they're independent objects? Is it or?
They're independent. So if you calculate the 2-point function, they vanish. These guys really are orthogonal. And there isn't a natural product rule. I mean, I guess you would like to see product of something with 1 row times something with 1 row give me nice and cleanly something with 2 rows or something like that.
And it should only work at large end.
Right.
It should not be an exact thing.
Okay, so well, I should check that. So no one has actually checked that. Who knows? I mean, there probably is something like that. Yeah.
It would be really nice, right? Because we know what to do when small. That's traces.
Yep.
What is the analog of that for operators in dimension?
Right.
Can one find a clean product basis? Can one show, as Gautam was saying,
Yeah.
that in this basis the interactions are small?
Right. Right.
So, but there is a condition that you have to truncate it. Like when you have a height equals n, right?
Yep.
So in that sense, you would if you take products of these large operators, large shoes with.
You mean at some point it should truncate?
Yeah, then there will be relations kind of that time. When you
Yep.
multiply, you will get things and then you have to truncate again.
Yeah.
So the relation has been accounted for by truncation. So that is where the non-Fox space is.
The non-Fox space. But you think that there actually is a genuine non-Fox space that's important even at large end? Suppose I
But
take.
you want your operators to be comparable, right?
Yeah, so suppose I have operators all of up to 1000 energy 1000 times again.
Then you presumably would not hit this problem.
I don't know. Well, I mean, it sounded like you would because even at 2 10 you hit this.
Yeah.
But still, I feel that there should.
Oh, are you thinking about taking columns and multiplying them or rows?
Columns.
Columns.
Yeah. I see what you're saying, but it should be because from the bulk,
Mm-hmm.
these things should be independent.
Yeah, yeah.
There should be a way of thinking that makes them.
But maybe if you do it this way,
Maybe.
then you can.
I was thinking actually
Yeah.
each column is one brane. Yeah.
Yeah.
And then you've got many columns, that's many different branes. If they're the same size, they've got more statistics. That's.
Yes, yes.
They've got different sizes,
Yeah.
I know, but what do I do?
So the product rule would be the standard multiplication Venn diagram with the cutoff,
Not for these guys.
even for the half PPS guy.
For the hot PPS guys, it would be. Yep. Yeah. Standard products of Young diagrams. Yep.
I think it would be really nice to get something like this work. Because everyone's made a big noise about large N gauge theories becoming strings. Those are the traces.
Yeah.
But we also know that large N gauge theories become E-branes.
Yes.
And there's been a lot of papers about that, but nothing real, right?
Yes.
It would be really nice to be able
Yeah,
to
yeah.
do something precise.
You mean see this Fox space?
You've seen the Fox
Yeah.
space that to be able to do calculations.
Yeah, 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 yeah. Yeah.
Okay.
Good. Okay. Now.
We never published this. We have this 20-page notes of the solid real answers. We never published. Giant.
So one thing that I want to just introduce now is an actual representation of the symmetric group. So let's say you have got this representation. This is a representation of S6. And one way to get the basis of states is to fill the Young tableau with integers from 1 to 6. And the rule is, as you move outwards along each row, the integers must increase. And as you move downwards along each column, the integers must increase. And then the way the representation is usually specified is you take an adjacent permutation, a swap. So this is a 2-cycle. It will swap 4 and 5. But the two numbers that you swap need to be next to each other. So I'll give you a rule that will work for 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6.
So I'm not understanding what you're giving us the rule for.
Okay, so what this is a state. This guy has a dimension of 16, and there will be 16 such Young diagrams that you label according to those rules that you increase and increase that you can write down. Each such state is a vector inside the vector space carrying this representation.
Oh, I see.
Yeah.
So you're labeling the Hilbert space.
Exactly, exactly. I'm now going to tell you this element of the symmetric group that swaps 4 and 5, how does it act on the state?
And sorry, how will you spread those numbers, these 1, 2, 3?
Oh, so I just sprinkled the numbers in there, making sure that I always increase going this way and decrease coming down. So for example, this representation is dimension 2. I can go 1, I can put the 2 there and the 3 there, or I could go 1, 2, 3. And those would be the two states inside this vector space.
And that's somehow you accounting for symmetries, that this rule of that you only increase, only decrease.
Exactly. So yeah, so this is Sn. So we don't symmetrize and anti-symmetrize along the columns, but
some.
yeah, exactly. Good. Now.
And if I count the number of ways of doing this, I'll get your hook rule.
Exactly. Precisely. Yes. Now, there's something else that we need. So there's a set of numbers that people call the content. And the way that you get the content, sure.
The 4, 5 with that?
Oh, this 4, 5. This is the element that swaps 4 and 5. Yep. And the rule that I'm going to give you will work as long as you've got an adjacent permutation. 2, 3 would be okay. The content, you put a 0 into the first box, and now you add 1 as you go this way, and subtract 1 as you come down. And you could fill the content into an arbitrarily big Young diagram. What will happen when you act with 4, 5 on this is you will get the same state back, but you can also get the state where 4 and 5 are swapped. And now I need to tell you what are the two coefficients. So the coefficients are 1 over. Now you should take, so let me see, good. You should take the content of box 5 minus the content of box 4. So in this case, the content of box 5 is 0, and the content of box 4 is 2. 0 minus 2 minus 2. So this coefficient here would be minus 1/2. The coefficient here is the square root of 1 minus that coefficient squared. And that would be the rule. So I'm just telling you what the rule is. By the way, so this was written down, I think, by Young himself. And people thought this was impenetrable, his proof. I don't know how long it was. The simplest proof for this, or the first kind of proof in sort of mainstream math that people used, was given by Vershik and Okunkov, and it was done in 1998. So this is very recent. I mean, you wouldn't have thought for such a trivial thing it would have taken so long. But
explicit matrix construction of this representation.
Exactly, exactly.
It's totally explicit.
Exactly.
Amazing.
1 minus 1 over C5 minus C4 squared. So now what I would like to do
And you can
is
check that this obeys.
absolutely, yep, and it just works perfectly. And build the matrix, take the trace, you got the character, whatever.
Yeah.
Yep. Now, we would like to start knowing how do we exploit large N. So how are we going to get some simplifications for large N coming about? What I'm going to do is the following. I'm going to imagine that, so I need to tell you what are the labels R,
When was
R,
young, by the way?
S.
Was he this century, last century? When was he young?
Good. Are you Googling, Abhijit? Okay, good.
It takes like, say, 100 years for somebody to find him.
Absolutely. Yeah, yeah. Okay, so I have to give you those three labels. So I'm going to think as follows. Here is the Young diagram R. So that's enormous.
In 1900s, he was young.
Okay. And the number of boxes, so R will be a partition of N, and S will be a partition of M. And the first simplification that I'm going to do, I'm going to imagine that N is very much greater than M. And the reason why I'm doing that is, if I had no Y's at all, and you ask me what is a Young diagram of 3 rows, I would say, well, this is 3 giant gravitons. So if I sprinkled in a few Y's, well, I still think it's 3 giant gravitons. Okay? So that's what we're going to do. And then I'm going to imagine doing the following. I'm going to pull off some number of boxes. Let's say I pull off just 3 boxes. Okay? 3 boxes here, 2 there, 2 there. So in this problem, I'm going to imagine that the number of Y's, so M, so this is the number of Y's, and this is equal to 1, 2, 3, 4, 5, 6, 7. So only 7 Y's, and the number of N's, the number of Z's, this is order N, so enormous. So this is some very small perturbation of these 3 giant gravitons. And the next thing that I'm also going to do,
Why are you calling them 3 giant gravitons?
oh, the 3 rows here, I'm imagining each row is a D-brane, actually a dual giant graviton, so it's gotten big in the ADS space. And yeah, those are the 3 things.
The height is 3.
The height is 3, 3 rows, exactly. So exactly, so 3 D3s.
Yeah, 3 dual giant gravitons.
3, exactly, yep. Yep. And good, so we've got that. I'm going to do something else as well. I'm going to imagine that this distance is enormous. So I want to separate these giants, and this is exactly in space. So I would expect now that this should be the simplest thing to study. I would expect to see some simplification coming because these row lengths are large, for example. And what is the simplification? Well, imagine that we've got 1, 2, 3, 4, 5, 6, 7. Sorry, I'll stop my labeling now. So now it's exactly the opposite of what the mathematicians use. Everything should decrease instead of increase, but it's easier to pull boxes off like this. And now let's imagine that we acted, say, with 1, 2. So I want to swap 1 and 2. Here's box 1, there's box 2. What is the difference between the content of box 1 and box 2? 1. So if the difference between them is 1,
Does the content also change in your rules?
no, keep the content the same. Yep. So the difference between the 2 contents is 1. So this coefficient will be a 1, and that coefficient will be 0. So if I act with 1, 2, nothing happens. Now let's try to act with 3, 4. Okay? So I don't want to know exactly what the content is, but could you tell me what would be, let's say, C3 minus C4? How big would this number be? Let's say this is, I don't know, order N. 4, go up, add 1, and now we have to go all the way across. How far? Order N. So we've added order N. So this thing itself is order N. So the first term here is 1 over N. I can forget it. And this is 1 minus 1 over N squared. I only get this term. So in this limit, there's a particularly simple action of the symmetric group. The numbers just swap around. Now, a consequence of this, that I wish I had a simple way to show you this, but so far I can only do it with a concrete calculation. But a consequence of this is that the number of boxes that I pull off each row is fixed. It doesn't change. Okay? So what that means is I might have one box going from this row to this row, but it will always be one of the boxes that belongs to little r, and I will still have 2 boxes removed here and 2 boxes removed here. The only operators that can mix always have 3 y's pulled off the first row, 2 off the second, and 3 off the third. Now, so that just happens. Now let me invite you to think about it in a certain way. So these are 3 giants. Dual giants. Yes. So these are 3 dual giants. Each of these boxes I'm now thinking about as an open string. At large n, I should expect the pattern indices are conserved. So I would expect that I can't pull an open string of one giant and stick it on another giant. And that's how I'm going to interpret that. Okay?
And this mixing is under this.
Exactly. Under that dilatation operator. Exactly.
Right. So you're saying we get a spectrum for each of the giants.
Spectrum for each of the giants. Number of boxes in each one of these is fixed. So now you might ask, if we wanted to get the operators of a good dimension from here, how could we do it? Okay?
But this rule was for adjoining 2 cycles, right? 4, 5.
That's right.
But out of this dilatation operator may come 1, 6.
Absolutely.
Then you want to do that.
Okay. So if you give me 1, 6,
Okay, you do this thing, yeah, okay.
I'll write it as 1, 2, 1, 2, 2, 3, 2, 3, go all the way up to 6. Yep. And then I'll just use the adjacents. Yeah. Okay. So now, what is my conserved quantity? I'm going to start saying I've got M1, which is 3, and it's telling me how many y's there are on the first row. M2 would be 2. M3 would be 2. So for each row, I've got a certain number of y's, and that's not going to change. It's like a new conserved quantity. Good.
And the energy will be the sum of energies for each row.
Yes. So now, what you can see is these are fixed inside each row. And the second thing is, if I was to act with 1, 2 on this, nothing changes. If I act with 2, 3, nothing changes. So at the end of the day, what happens is the following. I've got a new symmetry. So before I had SM, but because of this new symmetry, what I should actually be studying is SM1. I should be modding out by SM1, M2, M3, going all the way. And the same thing on this side. And the reason for that is, if I think about my restricted character, okay, which I've now removed. So if I think about my restricted character, this was some state, Rs and so on, gamma R of sigma, and some state sitting here. And what we're saying is, if we pick any element of SM, so the guys that are moving just the y fields around, if we mix boxes just in a single row, that's a symmetry. It doesn't change anything at all.
Now what about moving the z fields?
So
Is this row-wise decomposition maintained for those as well?
no. So in actual fact, R will change, a little r will change, but kind of the difference between them stays fixed.
Oh, that feels a little counterintuitive, right? Because you would have thought that each dual giant has its own thing.
I know. Yeah, that's true.
So when you looked at this dilatation, you said that one box can move also, right?
Yes.
What happened to that movement of this box?
So one box would always be allowed to move around. Okay. What happens in this limit is the number of boxes that can move around is even further restricted. So a Z box can move from this row to this row, but the Y boxes are fixed. So you are allowed to have a box from here jumping down to there, but the number of Y boxes is still fixed.
Why can't Y boxes jump around?
Actually, I wish I had a simple way to tell you. This is explicit computation shows that, and it's just go ahead and evaluate it, and that's what you find.
Robert, in 8 minutes I'm going to have to go. Just
Okay, no problem. So let me try to get to the punchline, which is, okay, so how could you build an object like this with these symmetries? One thing that you could do is, for this particular example over here, let's draw a dot for each row. And then for all of the left indices of the restricted character, I'll draw an arrow going in. I've got 3 things there, so I'll go 1, 2, 3. And for all of the other indices, I'll draw an arrow coming out. 1, 2, 3. And then I can do the same thing with the boxes 4 and 5. And I can do the same thing with the boxes 6 and 7. Now if I swap the 1, 2, 3, the 4, 5, or the 6, 7, that symmetry is manifest. I don't change the dot I'm landing on. And the same thing for the arrows moving out. And now what I'll do is I'll start to connect these things up. So I might connect 4 to 3. Then I might connect 3 to 6. And I might connect 6 back to 4. I'll join up all of the edges. Maybe I'll connect the 1s, connect the 2s, connect the 7, connect the 5, something like this. So that'll give me a permutation. So I can now again label these things with a permutation, and I can ask, how many graphs of this type can I draw? And I can count that. The number of graphs of this type I can draw matches the number of different values S and the multiplicity labels can take. So that first of all matches. And then what I can do is, this thing is a double coset. I can define the Fourier transform on that double coset. When I've defined the Fourier transform on that double coset and I take it, the resulting object that I get is an eigenstate of the dilatation operator. And when the dilatation operator acts, how it looks is as follows. So I'm going to flatten that graph out. This is maybe the last thing that I'll write.
Was that a non-trivial statement that you just do this group theory stuff and then it diagonalizes the dilatation operator?
I think so. So yeah, we were surprised when we saw that. So, I mean, in the spin chain, if you diagonalize it, you have to do some work. Here too, you have to do some work. And the Fourier transform on the double coset has some, I mean, it's got some work in it to define it.
But it's all symmetries, right? It's all, you don't really have to do any work. It's just group theory.
So that's right. But if you say to me, prove to me that this will be an eigenstate, I don't know how to do that. We built it, we acted with the dilatation operator, and it was.
Yeah.
So it was just a guess, and it worked.
In spin chain, you go to the momentum basis, and that automatically is the energy basis.
Right.
Here also the Fourier transform does that.
But you know, it's not a Fourier transform in position. You're swapping a permutation describing that graph for a Young diagram S and 2 multiplicity labels. So it's, yeah. But this is what the dilatation operator lands up being, acting on one of these things that we call a Gauss graph operator. It looks as follows. It looks like minus G Yang moles squared. There is a sum over I less than J.
Will there be no interactions between the excitations? 1, 2, 3. There'll be no interactions. That's why it's
No interactions. Yep. And then we've got Nij of sigma, and we've got delta Ij. And what this delta Ij is, so delta Ij is d by dxi minus d by dxj squared minus xi minus xj squared over 4. So essentially an oscillator. I should tell you what xi is. Xi is a continuous variable. It's given by taking the length of Ri and dividing by the square root of n plus Ri. So if x changes, you're changing the length of R. What is Nij? If you take some graph and we put maybe a directed graph that looks like this, let me rather change that, maybe this, we'll call that 1, 2, 3. Then for this problem, n1, 2 would be 1, there's just one edge going between the two. n1, 3 would be 3, and n2, 3 would be 1. So what's happening now is graphs label the eigenstates of the dilatation operator. The number of edges floating between the nodes of the graph actually appear in the form of the dilatation operator. And at the end of the day, you are diagonalizing a set of oscillators to get the anomalous dimensions. And this we checked in a lot of detail numerically. So this smells like you're starting to see giants with open strings attached.
So this is for a particular graph, this graph?
This is for this graph, yep.
But you
For this,
said you
for this
draw
graph.
all the graphs with this property or something, right?
Sorry?
You were talking about drawing all the graphs of this problem.
Exactly, yep.
So which graph appears here?
So this Nij of sigma, okay, I would read off the graph for any specific graph that you draw.
But
I-
the answer, sorry, I'm a bit
Yeah.
confused. You should get just one answer, right? You're saying it's invariant, doesn't depend on the graph?
Oh, it depends on the graph. So for example, if I had a different graph that looked like this.
But in this case, 3 to 2 case, it's always this graph.
Oh, no. I can join up the sides any way I like. So for every element in this coset, in this double coset, I will have a graph. So the number of graphs I'll have is the order of that double coset.
And which graph appears here?
You mean for this one? Pick any graph you like. The Nijs will be read off from the graph, and the graphs label the operators of a good scaling dimension.
So this is the dilatation operator acting on one particular
Exactly.
eigenoperator.
Exactly.
Each graph corresponds to
And what was the answer? What was I missed? What was
So the answer for the energy is minus g angle squared. This Nij of sigmas, the permutation describes the graph, and a delta Ij. This delta Ij is basically a sum of oscillator type things that you can diagonalize quite easily. When you diagonalize it, these x's are the row length of these Young diagrams. So you're actually mixing different row lengths to get something of a definite energy. And the Nij of sigma, this you read from the graph. So it's
And sorry, do I see that if I had, instead of 3 things on the first guy,
Yep.
if I had 4,
Yep.
do I see that it's somehow that these excitations are happening one by one? Is that true?
Oh, yes, that is true. So what do you mean happening one by one?
Meaning that the energy above the ground state
Yep.
is some excitation plus some other excitation, and these are
Absolutely, you see that, yes. So you mean that they're not interacting?
Yeah.
You see that.
That's not clear from this formula. I mean, here
Oh,
it seems that
so-
all the XIHs are these are like coupled oscillators.
So these are coupled oscillators, but what
And there's
happens?
cases in which they become like
Exactly.
one kind of
Exactly.
So what is the dimension of the Hilbert space that you are diagonalizing?
You mean, okay, so the graph,
In terms of this del by del x,
okay,
where is this actually?
so this is diagonalizing on the capital R and the little r labels. So this, in the large n limit, is infinite dimensional. At finite n, it would be some finite thing.
So you get a spectrum. Does that depend on the size of the row?
Yes,
So 1 over the size sets the excitation.
exactly.
So it's like spherical harmonics. Do you see?
It is like spherical harmonics.
Do you see No, you
So-
don't, because there's only one.
Yeah.
Do you see, well, if you put in all the scalars, presumably you'll see.
I hope so. Yep.
Do you think it will actually be slightly harmonics?
So that's one of the things that we've been trying to show. So to describe sort of, some brainwave.
And these interactions, these excitations, of course, at some order they interact.
Yes.
That's down in 1 by n, you say?
Exactly. Yep.
I see. And I see.
So the 1 by n interaction will let you move from one graph to another graph.
I see.
So it looks like a chant pattern index.
I see. And do you think that you might be able to see some locality here? It sounds quite remarkable. It almost sounds like you're trying to build the D3 brain
From the CFT.
from the CFT.
Yeah.
I'm not really seeing the chat pattern. What are the two in this? What are the two
Okay.
ends?
So the two ends, each one of these, okay, so there's a symmetry swapping these around. Each one of these is one of these endpoints, and what they are, so you can really trace these back. There's a symmetry under. We would have, say, let me say yi1 sigma of 1, yi2 I sigma of 2, yi3 I sigma of 3. This 1, 2, 3 and the lower indices would really correspond to the boxes sitting there. And in this picture, the upper indices would correspond to lines coming into a node, and the lower indices to arrows going out of the node. The fact that the number of arrows coming into the node equals the number of arrows going out of the node is the Gauss law, looks like the Gauss law constraint for the giant. And that's where the chant pattern.
So in the end, you've got a spectrum that looks like a product of excitations.
Yep.
Are you interpreting each of these excitations as being an open string?
Yes.
And how do I see the chat patterns of that? There are n square different kinds of excitations?
Yes.
I see. There's a spectrum times n square. Something.
Exactly. Yep. So that's where you're seeing it.
I see. And of course, you don't see strings stretching between the two brains because they're so far separated. Or do you?
Well, you shouldn't, but you do. So this guy, where the strings don't stretch between the brains, that guy is actually BPS because all of the Nij's vanish. So this thing just vanishes. But if you start stretching them between the brains, you see exactly that.
Those are what you're saying. Everything non-trivial is in these guys.
Exactly. The other thing is you can draw a picture of this on the LLM plane because each of these giants will be orbiting at some radius. And then the size of the energy is the difference between the distance, the difference of the circles that the brains are moving on. So that energy matches what you would expect for an open string.
And this harmonic oscillator, are you thinking of as the vibrations of the open string?
Of the brain,
Of the brain.
yeah.
What about the open strings themselves doing?
So, yeah, that's a good question. Each open string is a Y, so it doesn't really wiggle.
It's
But
too small.
exactly. But you can stick more stuff into each box if you liked.
It's like a ground state of the open string.
Exactly. Yeah.
Just moving.
Exactly.
It's weird that this brain is wiggling, but these are kind of not doing anything.
Yeah. So we diagonalized first in the S and the multiplicity labels. That's what the graph did. And then we diagonalized in these labels with the oscillator.
I'm going to have to run.
No problem. Okay. So that's all I'm going to say about matrices. So maybe this is a good place to stop. And tomorrow I will talk about CFT and how do we use symmetric group to build primaries in CFT. 11:30. Great.